Uh, Good afternoon, guys. Today, uh, we'll see what is the application of bypass diodes and like what is its application in solar panel, and then in what way it is protecting the panel, or how we are going to utilize this diodes. See, if you look at in this like picture 1 and 2, we have uh, some shades of leaves. So this area, and then if I take this and this area. So since this is like a roof panel, so they have most of the leaves has been like it's been shaded by the trees or leaves. Now, since we were dealing with the solar energy, so we think that whatever the all the panels, like if I have like 4 panels, okay, so even though you're getting the solar energy from all equal directions, but it will not valid for all other solar panels. Okay, so in general it will not be same. So some parts are, even if your vehicle, which is the roof of your vehicle, if it is parked in a shaded place or in some any other uh, area which you don't get any heat or solar energy. So in that case, the whatever the energy produced by your solar panel will not be equal. So let us say, so if I have 4 panels, so even if it is 2 panels are shaded, so don't think that all the 4 panels, since 4 panels are there, 4 panels equally will be generating the power. So that's not the case in solar panel. So actually this has some like environmental factors. It depends upon some external factors. Uh, External factors like we have environment, then like temperature, the temperature variation, and then it will depend on the humidity, and then the positioning of your solar panel, and then degree of solar radiation. So how much degree of the solar radiation is degree of solar radiation. So all these factors has an effect on the power generation of your solar panel. So eventually all these factors will leads to the power degradation. Power degradation, right? And this power degradation is also depends upon how much, like the degree of the solar panel is shaded. So let us take, if I have a solar panel of this size, so if it is shaded this region, there will be the output will be drop at certain level. If it is shaded this much of region, further it will be drop. If it is shaded too much, there will be further more drop in power output of the solar panel. Since in general we think that all the 4 panels are there, we will not get the equal contribution of all the 4 panels. If it is shaded, so definitely there will be a power drop in that particular panel or in that particular array, in that particular sequence. So that's why this shading has an effect on power output of the solar panel. And this shading can be of, uh, it can be fully shaded, or it can be of partially shaded, right? So depends upon the degree of its shading, the power degradation will be depends on that, right? Now, how in this scenario, how the performance or the output of your solar panel should not degrade. So, in what way we can protect these power loss? So we don't, since these factors are external factors, so there is no way to escape from these factors. So somehow through the electronic, the some devices, we can bypass this kind of power losses through this bypass diodes. Now, for example, uh, yeah, see here we'll take three cells, three solar cells, like without shading. It means that all the three solar panels, so they have a complete, they're like uh, they're receiving the solar energy in completely. It means that directly it is falling on the solar cell or panel. Now these are connected in series. So we have cell 1, cell 2, cell 3. Now, how do we know that this is connected in series? So, by means of the connection of electrodes. So, the negative and the positive and negative of positive electrode of first cell, and then negative electrode of the second cell connected to each other, and similarly the second and third also. And each cell is able to produce 0.5 volts. So that is uh, VOC, that is 0.5 volts, and V2 and V3. And this, it can able to also produce the current, the short circuit current, that is uh, we can take like 4 amperes. So since this is connected in series, the voltage will be added up and the current remains same here. The voltage is added and the current is same. There is no change in current. Now, if you look at the IV characteristics, so the IV characteristics of this particular series. See, the first solar cell, it can able to produce 0.5 volts. So that's what it is marked here, 0.5. And let us say the current will be of 4 amperes this side. Now this is the behavior of the first cell. Since the second cell is also able to produce 5 volts, it will be added to the previous cell. So that's why, so 0.5 plus 0.5 sum up gives to 1 volt. So it is extended here. Similarly, the third one, that is 1.5. So total voltage is equals to 0.5 into 3. So that is 1.5 volts it can able to generate. Now we need to plot the maximum power point. So that is the power output is the VOC into ISC. So which gives rise to 1.5. That is the total voltage into current 4 amperes. Total it gives to 6 watts. So this panel or this series combination is able to produce a power of 6 watts, right? Now, if I plot vertically here, so it will be somewhere 6 watts and it will be marked here, and this will be actually it is able to supply the maximum power point. This will be your I max, and this will be your V max. So these are the without no load conditions. So if you plotting, the maximum region will be much lesser than the ideal. Okay. So this combination actually gives this 6 watts. And this case is without shading. Now we'll see that what happens if any one of the cells, either it may be cell 1 or cell 2 or cell 3. So any one of these three cells, if it gets shaded fully or partially, so what's going to happen? Yeah. See, now the same scenario of our earlier case. So we have cell 1, cell 2, cell 3, so which are connected in series. And now cell 2 is shaded. So cell 2 is shaded. It means that uh, some it is either it can be of partial or fully. Now earlier the power output was 6 watts. Now since it is shaded one of the cell, the power which we get, the overall power output will be less than the 6 watts. Okay. Now we'll see that how it will be happens. So, so this is shaded. So cell 1 which can able to produce 5 volts. Since this is shaded, so ideally we are taking it is 0 volts, and then cell 3 as usual it is producing 0.5 volts. Now since this is in series connection, the voltages are added. The corresponding graphs, the IV characteristic is drawn here. This is cell 1, cell 2 and cell 3. See, as we discussed earlier, only cell 2 is shaded. So it means that only V2 is 0. So by ideally V1 plus V3, definitely it should be equal to 1 volt, right? But though it is not in the graph, it is representing still at some higher value. So if it is like 1, it will be less than 1.5 volts, right? So even though the graph, so since this ideal case, so we are getting this. So there is a voltage drop here, so it can be neglected. But here V3 also should start from maximum power. Like ideally, if you are speaking, it should be able to produce 4 amperes and 0.5 volts of voltage. So again, it has to start from here, right? But actually, this is not happening here. See, the curve actually it bends. See, the curve it is bending here, and it's somewhere pointing the lower maximum power point. Earlier, it can be of somewhere in this region. It is dropped here. Now, why it is dropping? See, this is the current direction, right? So it flows in one direction, and we are getting the output. But if you look at here, what is happening is the current direction actually it is reversed, right? So though if it is not functioning, it should ideally it should pass the current, and then we have to get it. But since it is shaded, what happening is the current direction is reversed. Now, why this current direction is reversed? Okay, so even though if it is reversed, but how the cell voltage still we are getting like higher region. So ideally, if you are speaking, if it is V2 is 0, we have to get only the total of 1 volt. So we should not get 1.5. So this is since we are speaking V2 is 0, so this should not happen. Only 1 volt we have to get. So here comes the your bypass diodes. Okay. Now, so the bypass diodes. See, diode, so we know that, so the shape is this. And so this is your uh, cathode, and this is anode. Okay, this is negative and this is positive. Sorry, this is positive and this is negative, right? Now we have to take the diode into the picture. Now, what this diode actually do? So it is a kind of like it will act. Let us take like one-way valve. So we can connect through this. So what happens is it can only allow the current to flow only in one direction. At that time, it will be acting as a conductor. Okay. Now, when the current comes in opposite direction, okay, so it will be acting as a infinite resistance. Okay, so it will not, at any case, it will not allow the to pass the current in opposite direction. So it will be blocking the current in that opposite direction. So that's how it functions, right? Yeah. Now, uh, since we are taking the case of shading, we are incorporating the bypass diodes, which are connected parallelly, parallel to the cell. See, and it also reverse biased. So I hope so you know what is meant by reverse bias and forward bias. See, same series connection which we have here. Uh, we'll get the power, the current flow in this direction, and cell 1, cell 2, cell 3. And parallelly, we have bypass diode 1, bypass diode B2, bypass diode B3, right? Now, this is the positive terminal, negative, positive, negative, positive, negative. Since the negative terminal of the cell 1 is connected to the positive terminal of the bypass diode, the diode 1. Same thing happens for cells 2 and 3 also. If you look at the current direction, see the current flows in this direction. So even though it can flow in this direction also, okay. So there is since it is in parallel connection, it won't there won't be any much losses. Now once the cell produce current, so it will be passes here. Now here also the current can be divided in this direction and in this direction. Now once if the power current goes here, and it can go in this direction and the reverse direction also. But since we are incorporating the diode in reverse bias mode, it will be blocking the power to flow in opposite direction. So there won't be passage of any current I1 in opposite direction. Now same thing, it flows, it goes here and then goes in all the way and will get the same current. The current remains same, right? So this is how we uh, produce the like protect the bypass diode protection. Now, like this is unshaded one. So this series connection is not shaded. Okay. Now we'll take an example of which the shading is there. Yeah. Now for the same example, we have a series connection with in shaded. So the current passes in this direction, I1, and so here your positive, negative, positive, negative, positive, negative. So B1, B2, B3. Now the current can go here and here and here. Yeah. Now we have fixed that the cell 2, that is, it is going to produce voltage of 0. So there won't be any uh, current or voltage generations here, right? Now what happening is sometimes this shaded cell, because of a continuous in absent, it will also sometimes it is referred as a bad cell also. Okay, so I'll tell why it is called as a bad cell. Yeah. Yeah. Now if you look at here, if you look at here, the current direction is changed in opposite direction. Now, why that current direction is changed in opposite direction? So that's the question in front of us. Now, we know that, so this is a semiconducting material, right? So it is having a PN junction diode, PN junction. So by doping the some materials, like now what happens is when it is in this direction we have current flow, since this is not able to produce any current, so the I is 0 and V is 0. Instead of it is producing or generating the current, what it does is it will be actually dissipating the energy, dissipating the energy. How it is dissipating the energy? So we'll see that. See, continuously in this direction we are getting current. So ideally, so this also should be in opposite in this direction, same direction. At certain point, what happens is the voltage which is produced by cell 3, what happens is it is also it is converted into reverse biased. It means that it is producing the negative voltage. So negative voltage in sense, so if you look at the power formula, P is equals to V into I. Okay. So since there is a drop in current, so somehow we need to manage with the help of voltage alone, right? So if there is some amount of amperes drop in current happens, at least by managing the voltage, we can able to maintain the power output same, right? But even though we are not able to maintain this 0.5 voltage evenly, why? Because since the at certain point it is going to shift its mode to reverse bias and then producing the negative voltage at both the terminals here and here. Then what happens is the current actually it is reverse. Okay, the flow of electrons somehow it will be attracting the electrons in this side. So there won't be any like if you look at the, it means that at at the edge it will be acting as a strong resisting, right? So because of that, your current direction flows in opposite direction, and the negative voltage refers to the power dissipating to cell 2. So when this continuous dissipation happens in the both the directions, actually at one point the cell 2 will be overheated, and eventually it becomes the hot spot, and then it will be burned like burst, or it it will not work, it will not function, right? So this is how your shading can actually convert a good cell into a, as I said earlier, the bad cell. Okay. Now, in that scenario, we are incorporating the bypass diodes. Uh, see, now, as earlier case, the current direction will be here, and then here V2 will be 0 actually, right? Ideally, we have told that. And the cell 3 will be acting as a negative, it will be generating negative voltage. Now, once the current flows up to here, since this is not able to generate any current or voltage, so there will be surely droppage of current. Now, at that point of time, this will be acting as a forward biased. Forward biased, right? So then the current can able to go in this direction, and it comes here. So this is the direction of current. So I'll make it clear here. So in this direction, and then it goes as usual, right? So even though the cell 2 is blocked, as we told, the current cannot go in reverse direction. So IR is blocked. Since it will be acting only forward bias. In that case, again it will be acting reverse bias, and there won't be any passage of current. So there won't be any flow of current. And in that case, it's the same current will be getting throughout the circuit. But so definitely there will be droppage in voltage. So V2 will be, so earlier we told it may be of 0.5 volts, but after incorporating the bypass diodes, the voltage will not be of 0.5 volts. So it can be dropped at certain percentage levels, and then uh, your power will be also dropped, right? So actually, this is how your bypass diodes will be protecting your uh, solar panel or array. Now, for how many, since this is connected in series, it is showing in such a way. But if you are incorporating a solar panel, then how many of such bypass diodes requires, right? So that's the question in front of us. So why? Because so these diodes are costlier, then we cannot incorporate for each and uh, for series of strings, right? So there should be some minimum number of diodes, like minimum cell quantity required to incorporate the diode. So we'll see that how many diodes are required per like cell combination. Yeah, 1 minute. Yeah. So Integrating of such bypass diodes is called as bypass diode integration. Diode integration. Okay. So actually, now how many diodes we require for us? Typically, a bypass diode across groups or substrings of a PV cells, typically 16 to 24 cells in the back of panels or within the junction box of a solar module can be provided. So for example, two bypass diodes are sufficient for a solar panel with a rated power of 50 watts. So if you're having a solar panel which are able to produce 50 watts, so you can use two bypass diodes. Okay. So by counting the number of cells in your panel, you can divide half of, so one bypass diode for each string of cells, and then second for second string of cells. So for this 50-watt solar panel, mostly will be having 36 to 40 cells. So, so this is actually for a lower, like mid end of your photovoltaic panels. If you go for high-end solar panels, for those high-end panels, they are directly fabricated onto the semiconductor photovoltaic structure itself. Okay. And then, so mostly this diode will be of use is these Schottky diodes. So I hope that you know what is meant by Schottky diodes. You might have studied in your electrical science in different types of diodes. So this is one. So mostly ranging from 1 to 60 amps, and then voltage up to 45 volts. So that's why actually, since the voltage is higher, mostly will incorporate in the uh, high voltage and series connected panels. Okay, so in that cases, we'll be mostly incorporating the bypass diode integrations, right? So this is what regarding your bypass diode, how it works, and then how it is actually producing the like protecting the other cells from not functioning. So and also from power degradation, right? So this now another one topic in the last class I have told also that since now the bypass diode eventually if it is like shaded bypass diode, so we know that now it is at some point of time it will be overheating, right? Now this overheating actually it means the increasing temperature, right? And also we know that the effect of temperature on IV characteristics, IV and PV characteristics of a photovoltaic cell or panel, right? Now, tell me that what happens if your temperature increases? In the last class, we have discussed this. What happens if your temperature increases to your voltage? So voltage will increase or will drop. So any idea? So in the last class, we have discussed, right, effect of irradiation, effect of temperature. So if you know, you just comment, give in comments. Any rough idea? Okay, fine. In the last class, if you just see the IV characteristics, so we have seen at temperature, sorry, at particular irradiation. So we have three different curves. This is T1, T2, T3. Okay, fine. So even in the beginning of the class, so we have discussed that. So if there is 1 degree rise in temperature, 0.002 volts will be droppage. So if this is 25, 30, 35, so corresponding values 1, 2, 3 volts. Now, see, it is affected in two ways now. Now the cell, now since it is in, let us take this is in shaded region. Okay, so one case is it is not receiving any solar energy, so there further there will be drop in voltage. Okay, now because of it, other factors which are influencing the performance of this cell, okay, it cause into overheat, right? Now why we cannot take in two that like 2 point of view we can discuss this. So in this direction we're not getting the temperature, but here in this direction it is overheating. So why can't this, like here there is a rise in temperature, here there is like since it is shadow we can consider there is drop in temperature. Then why both the things are not balanced here? So do you understand what my question is? See, actually, the concept of the solar cell itself, if this is solar cell, the radiation should fall onto the surface of your solar cell. Okay, but whatever this overheating and all, it is happening it is the like effect of the in other direction. So, but it does not mean that it will be like since the temperature is increasing here, it will not like it should not function. In that scenario, we should not think this. Okay, so keep this mind. So it has to be exposed to the sun, like solar energy. So it has to fall onto the cell. But these things are happening with the in other ways. Okay, so that's why, so this is will not be in our considerations, right? So this is what we uh, get this from here. So we'll just summarize what we have seen so far in the solar cells. uh, we have seen the working of a PV cell, and then we have seen like certain examples on uh, of solar cars. So like you have to compromise on aesthetics, compromise aesthetic features, and then we have seen possible ways of incorporating the solar panels, incorporate solar panels. And then we have started with the IV and PV characteristics of a cell and a panel, or we can call it as, sorry, not panel, an array, right? And then we have started the yeah, we have solved one numerical problem, numerical problem, and then we have seen the effect of irradiance, effect of temperature, and then we have started with the again the uh, bypass diodes, and then we have also seen the how to plot the maximum power point. So that is in short form MPP, and how to utilize the IV and PV curve to find the maximum and minimum parameter like voltage and current, and also with respect to the design parameters. Design in that point of view also we have seen. So up till here we have seen like how it functions and all other characteristics, and here we have seen the how to protect other cells from a bad cell, and not lose the how to not lose the power generated by a solar panel, right? And then next, so in next class, so will be like, since as we know that from day, so morning 8 to evening 4, so as the day follows, your temperature varies, right? So as your temperature varies, your power output varies, and this varies, your maximum PP will also vary. Now, how to trace this or track the maximum power point in a solar panel or in a series string of solar cells? Okay, so that we will see in the next class. Uh, so and then we have like efficiency, solar efficiency and cost comparison. So once we finish this MPP, and then we can go to the these topics. And then the efficiency of your solar panel is nothing but, so P output is equals to So the power output which we get is VOC ISC, and then if you just divide by P input, you'll be getting the efficiency ISC P in into 100, and then this will be multiplied by F form factor. So why? Because so we'll be having the losses. Okay. Yeah. So that's what the topic for today's class. So if you have any doubts, you can ask. So if not, you can leave. Thank you.